the Schwarzschild solution and the event horizon. Let us consider the case of mass m as the source of a static and isotropic gravitational field. Then, the geometric properties of the resulting spacetime are determined by the Schwarzschild solution, a metric tensor alpha beta. The line element, given in terms of Schwarzschild coordinates, x alpha equals t, r, theta, phi, is, c where for equals 1 minus rr, r equals 2 gmc2 denotes the gravitational radius and d omega 2 equals d theta 2 plus sin 2 theta d phi 2 is a surface element of a unit sphere. We will utilize the system of units such that c equals g equals 1. Solution, 2.1, is determined in an empty space outside mass m. Usually, when one deals with a weak gravitational field, the radius rm of mass m is much larger than its critical radius, rmr, than fr1. Actually, for the Earth, re 6 mm, the strength of the gravitational field is of the order of 10⁻⁹, the strength of the solar gravitational field is still very weak, 10⁻⁶, but neutron stars yield strong gravitational fields, 10⁻⁻. Black holes are the sources of the strongest fields, where an event horizon, defined by fr equals 0, is developed. In such a case, we shall consider that the space outside and inside the horizon is empty, the mass of the black hole is confined at r equals 0 a singularity. This case will be referred to as an eternal black hole. We shall call the region outside the horizon as the exterior and that inside the horizon as the interior of the black hole. Exterior of the Schwarzschild BH. The meaning of a strong gravitational field is revealed via investigation of the properties of the exterior and then the interior of a BH. It is natural to start from the former region. Let us underline the first, nearly trivial fact that the relativistic definition of the gravitational radius as the singularity of the metric, 2.1, coincides with a purely classical physics definition of a critical radius such that the escape velocity becomes equal to the speed of light in a vacuum, c. The generalization of this observation leads to the conclusion that the speed of a freely falling test particle tends to c, independently of the initial conditions. This and the other properties of the exterior of the event horizon may be described by means of geodesics of both kinds, that is, for massive and massless particles, light rays. The geodesic equations may be derived from the following Lagrangian, c. 4. In a standard manner leading to the Euler-Lagrange equations, x mu dx mu d sigma and sigma is an auxiliary parameter. There are two conserved quantities resulting from the symmetry conditions, energy, E, due to time independence of the Lagrangian, and angular momentum, L, due to the invariance of the Lagrangian with phi. The latter condition results in the planar character of geodesic motions, so one may, without loss of generality, choose an equatorial plane, theta equals pi 2 and express these conservation laws as follows. One can determine then arbitrary geodesics from the normalization condition. Where eta equals 1 or 0 for time-like, massive object, geodesics or for light-like, massless object, geodesics, respectively. Indeed, the radial component of the velocity vector, u, eta equals 1, or the wave vector, k, eta equals 0, takes the form. Using Eqs. 6-9, one can characterize both types of geodesics and illustrate in this way selected features of gravitational fields outside the BH horizon. Apart from geodesic motions, we will also be employing systems of static observers, so, whose spatial coordinates are fixed. They are characterized by velocity 4 vector. Let us consider the situation of observer A, Alice, whose frame of reference is in a radial free fall, L equals 0 towards the BH horizon, 4. A's frame, or spaceship, initially was at rest at a mother station Mississippi, located at R0. The coordinate time to cover the radial coordinate range R0 R in this case is found from Eqs. 6-9 it diverges, t as A's spaceship approaches the horizon, RR. The proper time, which is the time measured by Alice herself, turns out to be finite. This illustrates a manifestation of the most dramatic time delay, for distant observers, but actually for all observers exterior to the horizon. Alice's frame of reference would need an infinite time to reach the event horizon, while a finite time elapses for the co-moving observer, Alice herself. Another aspect of this outcome has already been mentioned. The speed, v, of the freely falling test particle as measured by a static observer, so, follows from the expression, see also. One finds then a general outcome, the speed of a test particle radially freely falling. Approaching the event horizon tends to the value of the speed of light in the vacuum. And this result is independent of the initial conditions. One may ask, how would that speed be changing inside the horizon? We discuss this question subsequently. It is a well-known fact that due to the equivalence principle, an observer confined within a frame freely falling towards the horizon cannot identify the instant at which he or she crosses the horizon, and if a black hole is large enough, such an observer would harmlessly cross the horizon without even noticing. On the other hand, one can quite precisely determine that instant. How is this seeming contradiction possible? Before resolving this, let us recollect a well-known result, that of the gravitational frequency shift. In order to do this, one considers radial signals of a fixed frequency, omega macron emitted at r0, the location of the mother station, and recorded by a static observer at r greater than r. The wave vector k of those radial light rays, k equals ktkroo is, cx 6, 7, where plus or minus corresponds to out and ingoing rays, respectively. If ms emits such a signal with frequency, so records it at r and measures its frequency as so, o. The frequency recorded by so is indefinitely blue-shifted, when r tends to r, f0. When such radial signals are recorded by Alice, omega a equals uak, at her instantaneous position at r, then she finds, cx 6-9, and 15, 16 where v is the speed of her spaceship as measured by so, placed at r, c, 14. Exchanging such signals, one can observe a generalized Doppler shift of the following form. And the meaning of result 22 is as follows: signals coming from a frame in falling towards the black hole horizon are indefinitely redshifted, and ultimately disappear from the screen/sensors. Such a journey seems to take infinitely long for external observers. This confirms our former conclusion. The result, 21, on the other hand means that the Doppler shift of signals coming from ms allows Alice to identify the horizon quite precisely. The Doppler shift reaches a value of half on the horizon. With the speed of free fall tending to the speed of light in a vacuum, the generalized Doppler shift as characterized by x 21, and 22, and the dramatic form of the time delay in this case, this leads to yet another anomaly, image collision or touching ghosts. Signals emitted by Alice located within the infalling frame appear to get frozen in the proximity of the horizon, c. However, let us consider another observer, b. Bob, whose spaceship also starts from ms, following Alice's spaceship. Alice and Bob exchange electromagnetic signals. How, when, does Bob perceive the instant of Alice's crossing of the horizon? The answer has been referred to as image collision or touching ghosts, and it is as follows. Alice sends an encoded message, a signal that means I am crossing the horizon. At the instant when her Doppler shift is half, Bob receives that message at the instant when he himself crosses the horizon. An interesting fact is that this effect, originally illustrated by means of Kruskal-Seker's coordinates, may be interpreted in a general manner, without reference to any specific system of coordinates. Indeed, if Bob receives such a message before crossing the horizon, that information would be transmitted to our part of the universe. This would contradict the fact that the horizon crossing can never be observed. In the case of null geodesics in the equatorial plane, the wave vector components are as follows. Where b is so-called impact parameter, the function Veffer equals fr2 r2 is regarded as an effective potential for null geodesics, c. The shape of null geodesics depends on the value of b. The deflection angle is small for large values of b, light rays are only slightly deflected. It grows indefinitely as the impact parameter value tends to its critical value, BCR-1 equals Veffers. The impact parameter BCR corresponds to the so-called photon sphere composed of circular trajectories, R equals RPHS, which are unstable, null geodesics. Effective potential Veffer equals FR2R2 in the case of Schwarzschild spacetime, horizontal axis, expressed in units, RSR equals 2m. It should be noted that in approaching an event horizon, the shape of a light cone evolves in a characteristic manner. Indeed, observing radial in and outgoing signals, one finds, which may be illustrated as a sequence of vanishingly narrow cones,